Hello and welcome back to APL programming. So the shape this was in last time was like this, and I had an idea for making the expression for the index array in a different way. And it turned out to be quite short and elegant, so I would like to show this, and then also I thought when I'm at it already I would implement the alpha beta pruning. So this will be part of this video. And we will add some functionality here in the main loop and do a few other things and learn about tail recursion. So let's start with the index array expression. So the idea was that we take the four rows, horizontal, vertical, and the two diagonal forms, and add them to every single place here in this 6x7 matrix, which of course would give some positions outside of here, but then filter out the four rows that have invalid positions, and we should be left with all the ones that are inside. So first of all, how to construct these four types of four rows? Well, that's simply an array of this form. So if the first coordinate here is are the rows, right? Then these would be the vertical ones, the horizontal ones, the diagonal to the right, and upwards somehow. Well, it doesn't really matter. We could put the -1 also here, so this would be down. No, to the left. But doesn't matter. Anyway, these are the four different types, and now multiply them with this, and this gives these offset vectors. Let's put them in a different form. No, like this. Let's look at this with the display function. So these are now enclosed in these four vectors here, and now add them one after the other to all these coordinates here. And how we get these, we already know. This is this expression, and for adding each one we need it in this flat form. So, but if we add this right away now, well, let's try it. This gives an error, so we will still have to do something here. So add each one of this, but this is a length error. So we remember that if we want to add here something, it has to be of the same shape. So for example, let's add simply 10. Let's try with enclosing it like this. Okay, so this makes sense, since if we enclose this 2 times, the enclosement depth is equal, and then it can be added. Okay, added together. So we need to do this for this part, and since if this is already enclosed once, so we have to close it, and for each single one of them. Okay, so this is how it works. And now let's flatten this again and look at it. Now we see that we get all these 4 vectors, and quite a number of them is outside, has here coordinates that are bigger than what is allowed. And let's see how many there are. 168. So this is 4 times 42. Yes, makes sense, since our 4 types of diagonals, and 6 times 7 is 42. So, and we already know that we will have to filter out such a amount that 69 of them are only left. Okay, so how would we filter this out? Well, we have a nice function here, element member of. Let's take an example here. For example, number 123 looks like this, and we can see that this, the last one of it, or this already, is not correct. Let's find a correct one. No. This looks correct. Okay, so okay, we have a correct one and an incorrect one. So how would we distinguish them? Well, they should have all of them, all the 2 vectors should be elements, should be members of this set. Okay, and here we see this one has all of them in there, and here the last two are not in this set of coordinates. So to distinguish, we would just have to AND them, and these over these 4 entries, and this would give us these the answer if the entire 4 vector is correct or not. Okay. So we would have to do this now for every one of these 168 4 vectors, and for this we can use the dynamic function notation again. So this would be an omega, and we would apply this to each of this list that we already have. Let's try this. Okay. And now we see that there are quite a number of zeros and ones, and the number of the ones should be exactly 69. So let's add this together, and this seems correct. So this has worked so far. But we not only need this number of 69, but also the corresponding 4 vectors is what we need. So we need to select them. So this would look like this. So this entire list is taken as ones here, like it is, and then here is our selection filter, so to say, and it is these are selected. So now we have the 4 rows that have all the correct coordinates. Yes, it looks correct, and it's also the correct number, and we still need them in this form like this later for the for this index array expression. We need it in this form. So this looks correct, and it's done, I think. So let's try it. Oh yeah, one thing is left. This can be written shorter. Okay. So if we want to have a collection of such 2 vectors, and we have many of them, we can do it in this way, that we take all the first components and catenate each one of them with the second components. Okay, so this gives exactly the same result, but as an expression it's shorter. So let's take this, put it in. Still gives the same result. Okay, so let's test it in the actual program. quite a bit shorter and much more elegant, and also more general. For example, if we would decide to have 5 in a row or 3 in a row, this would just be a change here, or if we would have a different board size. This is still the one where the computer starts with a steps of 5. Okay, so this seems to work. Nice. Another thing is here, I noticed that this expression could be a bit slow, since this part here is evaluated even if it isn't needed. Okay, so it constructs this array here even if the entire array, even if only this part is needed, but we have a different way to compare this, make this condition here. If there's a 4 in this t in this point array, we simply return 1000 and then it's over here. Okay, so this returns immediately here, and only else in the else case this is evaluated. So in this form, first of all, it looks a bit better, and also it should be a bit faster this way. So now I promised, no, I didn't promise, but I had in mind anyway to do alpha beta pruning. So now, but I will not explain it, because it's on Wikipedia and textbooks and everything. So what I did is I wrote just a little basic program here that takes the standard implementation of alpha beta pruning, and first of all I translated the APL program exactly into in basic form. So here is the part where the maximum is determined. So this is this part here, and the for loop here goes over all the valid moves. Okay, so this is exactly this part. We determine all the valid moves, i.e. the columns, and apply this for each of them, and then find the maximum. Okay, and this is done in this loop. So loop over all the columns, and then if the column isn't full, do this, and then determine the maximum on the way. So this is done in one step here. And then if we look here, this is the alpha beta pruning implementation. And the thing with alpha beta pruning, why it saves time, is because this loop is aborted if here a certain condition is reached. So the question is now, how to abort this loop that is done here inherently, and with the each command this is not possible. Okay, so we have already seen here the power operator, where we can construct a loop and abort it. And now we will, learn a third, different way to make loops, namely with so-called tail recursion. So this will be a bit longer now and not fit anymore in this line. Okay, so tail recursion. It's easy. Let's do again some output so we can see something. Let's take an omega starting value again. And now the function should call itself. No, and let's stop. If omega is 0, count it down. And how do we call it again if we have no name for it? So there's this feature of the D function that we can do an anonymous call with this symbol, and this should already work, and it does. Okay, so return value is here this empty list, and this is another way to do loops. And since it is the recursion is here at the end of it, okay, the interpreter recognizes it and does not save anything on the stack and reuses the same stack frame. So there's no stack built up here because of the recursion. And this is a well-known feature, so other languages have this also. So this is basically a simple loop. Oh yeah, so let's immediately right away let's try to program this maximum finding. Okay, here on the command line with this form. So what we would have is we would have array of let's say some random numbers like this, and we want to find the maximum in here. Okay, so this would be 94, and normally this would be, oh, okay, no, this is, no, it's not good. No. This is a good one. Okay. So normally we would find the maximum like this. And now let's try it with this tail recursion form. So we would give this list, and we always need a starting value for the maximum. So this would be minus infinity or 0. But we always need this, and then call this maximum, the current maximum, and this is a list of values, and we will go through this list simply by testing the first element of the list, and then do the recursion with the list, with the remaining parts of the list. Okay, so, and then of course the recursion will end if the list is empty, and then we return the maximum that has summed up to this part. And so this remaining part of the list would look like this, and the maximum is simply the maximum of these two elements. So the current maximum that has been determined until now, and the first element of the list. Okay, so let's try this. This works already. Let's see what happens here. We can simply output these two variables. So this is what happens. Maximum is 0, and this is the list, and then it of course determines that the maximum of 0 and 47 is 47, and this is the new maximum, and this is the rest of the list, so it has dropped the first element. And then the maximum stays the same until it encounters this 58 and so on, and then encounters the 96, and it does the tail recursion until, so this is the last element of the list. The list is empty now, and then it returns the maximum. Okay, so this would be a way to find a maximum in a iterative way with tail recursion. And this is the form now that we will use for alpha-beta pruning. So if we look again here, what we will have to do is first of all give this val two new parameters, namely alpha and beta, which I will call here x and y, because b is already taken for the board. And the way this is initialized here is with starting values of -infinity and infinity. Let's take 10,000 for that. So this part here is will also be longer. And okay, so this initializes alpha and beta in this way. And here we will have to give it minus beta and minus the maximum. No, like this. Let's call m. So here we don't determine the maximum now with this form, but now with our maximum search. So again we will have a maximum and a list, and if the list is empty, we return the maximum, and else we determine this value so the list is the number of the list of valid moves, and for the starting maximum we take here alpha. Okay, so this would be x in our case, like this. And now for this part. Okay, so now if this value is greater than the current maximum, we do something. So if v is greater than the maximum, we do something, and inside here, so we set the current maximum to v, which is returned here, but this part we have already. Okay, so but this is the crucial part now. If this is greater or equal to beta, so we can simply beta was y, then return this as a maximum. Okay, so here the maximum is set to v, so this is how we would implement it here. We don't set m to v and then return it, but we simply return v itself. So this part here should do the same as this. And now for the tail recursion part. So again we need to return the remaining part of the list, and for the maximum now we have to do it like this. Simply determine the maximum between the current one and this value that has been determined here. Okay, so let's see if this works. Domain error. What is happening here? Of course we have here the part where we take the first element of the list. So this is of course not the omega of the an element here of the valid move list taken as omega, but this is now the head part of the list, and it seems to work. Yay! So if you remember last time it was quite a bit slower, and that it's faster now is only thanks to and it won. Okay, is thanks to the alpha beta pruning. So now this works, and what I want to do still is add this functionality here that it actually aborts when someone has won. And this is easy. simply call the point function here with a board and determine here if there's a winning situation, but if we think about it, we have to take the other player here, okay, like this. So we are here at a point where the board has been displayed, and now the remaining moves are determined, and from this the player whose turn it is. So the other player has put a stone in last time, so if we want to check for a winning situation, we would we need to check here for the other player. Okay, so let's test it. What? 3 minus s. We are bored like this. Okay. Yes. And it won, and now it's aborted. Okay. And we can use now that we know the how tail recursion works, we have an alternative here. We can do it equivalently here like this. So just return the new board, and this entire function is calling itself again with the new board. And so now we notice actually that this is actually equivalent. So this would be the new implementation of Connect 4 now in APL. We have now alpha beta pruning, the abort when someone has won, and so what would be remaining to implement maybe is make it stronger. So for example, that it recognizes threads here in even or odd rows, but this is not entirely APL specific. I don't know if I'm going to do this in APL. I've already implemented it in other programming languages, but we will see. So far, so again, I hope it was informative and you had some fun also with APL, and I won't say now that it's finished, because I said that the last 2 times and still had here ideas. So maybe see you next time, and thanks for watching. Bye.